that so in other words, if I take a point and take a chunk in that, and I want to see the twerk, are these twerk are performing some kind of rotation? You're gonna say, I mean, if yes, you're gonna say yes, there is curl, and if not, there is no curl. There is no curl. Are you getting the point?
यहाँ पर इसे करना चाहिए सर,
कहाँ?
डिफरेंट है सर यहाँ पे velocities particle
नहीं, भले हो वो डिफरेंस जो है ना यहाँ आ रहा है. Here you have kind of uniformity. You have kind of uniformity. So in other words, here's the thing. Another way would be to see the field vectors actually. Can you see a bit of rotation? You can't see. Maybe there are some points. Maybe there could be some point, but apparently, this has come 0. So it's like that's a gradient field. So what you're looking at is it's like a gradient vector. That's what what you call point character told us actually, that if you have a field in which you have don't have a rotation, you can find a scalar potential. Can you spot some points where you can find a curl where there are lots of points?
Yes, sir.
There are lots of points. Okay, there are lots of points. You have a less curl here. Okay, a less curl here because the particles are kind of moving with a uniformity. Okay, maybe you can have curl. Apparently it doesn't show that. But you have a more curl here. Okay, the magnitude of the curl is a lot. While as we are going away from this wall or whatever you call it, you have curl but less as compared to. So you have a curl. So I can pick a point and I can say that there is a curl. But for that curl, space is responsible, not the particles themselves. This is an important thing. The geometry matters actually. Space is the shape of the space that is kind of pushing the particles to move in a specific way actually.
पार्टिकल्स की वेलोसिटी भी हो सकती है ना सर, रीजनेबली कर्ल की भी. ये जो पार्टिकल्स मूव कर रहे हैं अगर इनकी वेलोसिटी डिफरेंट हो सकती है, कुछ तेजी से मतलब मूव कर रहे हैं और कुछ स्लो, तो सर
उसमें तेजी से मूव करें या स्लो मूव करें, ठीक है. The curl is there a rotation. So just think, you always have to think. So if I want to know how much of curl is happening here, just put a twerk and see that what happens with it. So obviously these particles which are here are moving faster than these parts, so it's going to produce some curl. And we can really see the curl detectors again. So you can activate, for example, this, the curl detectors. You can see that you have lots of curl here, but almost every part has a curl actually. Can you think about it? Almost every part has a curl. So it doesn't have a positive curl. And when something has a curl, it's going to have zero divergence. Because divergence is representing spread, while the curl is forcing you to move in a particular way. Thank you. Think about it actually. So divergence wants freedom to spread in all directions, while the curl is pushing you to move in a. So you are not allowed to spread too much. Okay. So you can have it. So these are like the curl detectors, and you can see that. Okay, you have curl here, a little quantity of curl. You have more and more quantities. As you are away from this middle part, you have less and less curl.
अगर एक वेक्टर फील्ड है, मान लो कि जो बात ले रहे हैं जितनी बॉडीज हैं, अब वो रैंडम मूव कर रहे हैं, रैंडमली, तो वहाँ पे सर
The randomness does not comes because they are random. The randomness comes because of the collision actually. I mean, think about it. If there is no particle, so we can have it. So this is we can do it. So let's assume that you have a very little number of particles actually. So you're not gonna see. You're not going to see that it's moving randomly. So one particle is going here and there, but so it just takes one part. Okay. It just follows one trajectory. I got the point. I mean, the real trouble is that if you have more and more and more and more and more particles, then their collision can influence can create the randomness. ठीक है? So I hope you got some sense of the curve. You got some sense of the curve and some sense of divergence. Now what is?
सर जब डाइवर्जेंस मतलब कि सर जब रैंडम मोशन होगी वहाँ सर हम डाइवर्जेंस को फिर कैसे मतलब कि वहाँ पे करेंगे?
रैंडम मोशन होगी तो डाइवर्जेंस कैसे?
जी डाइवर्जेंस फिर नेगेटिव पॉजिटिव.
No, I mean if you want to know the divergence, the real thing is that just see it from the perspective of vector field. That is going to give you the correct picture of what is happening, because this picture is telling you a particle, no matter what particle you is going to follow one of the trajectory of this. All these vectors actually, it can come here and go here, and it's going to follow one of the trajectories of it actually. Okay. Well, this is a good question in itself actually. It's something of very near to my heart because I do stochastic calculus. The stochastic analysis is all about making sense of the random things actually. If imagine you have thing is moving here and there. Okay. One of the limitations of the physics or the basic physical principles is that they assume that the universe is deterministic actually. Okay. Well, I argue universe is not deterministic.
Sir,
It's a stochastic universe.
आपने कहा कि कर्ल जो है वो नेगेटिव डाइवर्जेंस की रिजल्ट होती है.
नहीं. Okay. मैं ये कह रहा हूँ कि divergence and curl. You will see that if something is curling, that means that there isn't any divergence actually. Curl का मतलब ये you don't have a. मैं कह रहा हूँ कि देखें, you want to run away from the center, okay? You want to run away from the center, okay? But something is forcing you to move around the center actually. So think about it. You're gonna say you can't really go away from the center because there will be always something that is going to push you to move around it. Okay? And so what you are looking at the moment even is that it's a conservative field actually. Magnetic field is conservative field. Gravitational field is conservative field. Okay? So, it's a conservative field. Because they have rotation there. Okay. Anyway. Is it making sense? What about something I like? Last thing that I would like to talk is about the divergence. Now this is a very interesting kind of quantity, which is all you can also interpret as, that if you have a scalar function, a scalar field, you can talk about its divergence, which is going to be also going to give you the description of Fresh derivative. Because we know that gradient is a Fresh derivative actually of a scalar field. Okay. So what does divergence is telling you? Imagine I am sitting at one of the points. Okay, sitting at one of the point on this space. Now from this point, I can go in all directions. I can go here and here and here and here and here. So I can go anywhere. So I can move in any directions. Question: which is the direction in which I'm going to move faster, roughly. So imagine you are on the hill and you want to go down, and you want to take the path which is kind of the shortest. You want to take a sharp, really sharp kind of a track actually. Okay? Gradient tells you that. The gradient is all about that. Okay, you're sitting at a point and you want to know. So you have a surface. So the scalar field is what? I mean, if you plot it, you're going to get a surface, and you are sitting at some point of the surface. And on that point, I can go in many directions, but I want the direction of the maximum change actually. Okay? Direction of the maximum change. So which direction is going to be the direction of the maximum change? If I go this way, is this going to be the direction of the maximum change? Or this, or this? Along the surface is going to be. Right? This is going to be the direction. And you can see it actually. Like these are the, really, if your direction is really, kind of a more in line with the direction of such particles, you're going to say that's the direction of the maximum change actually. So you're sitting on a hill and you want to skim down to the land actually in a fastest way. Okay, and you want a map which is going to be the fastest way to reach down actually. And you want that map, so assume that hill as a surface and compute its gradient. And that gradient is like the map actually. Just follow the gradient. Okay? You're going to reach maximum. But if you are a professional, what do you call, if you are a professional player actually, okay, then you're going to avoid, the direction of the maximum change, because that would be really dangerous. Really dangerous actually. Really dangerous. Okay? Really dangerous. Correct. Jay? So it's better to take, enjoy and, rather than just in this manner, we're killing actually. We like the killing. Okay, is it making sense? Okay, so direction of the maximum change. And there was an exercise in your exercise sheet. I mean, if you remember, in an exercise sheet, there was an exercise where we said that, okay, if you are computing the gradient of any scalar field, prove that its direction is giving you the direction of the maximum change actually. It measures, gives you the direction of the maximum change. If you haven't done it, you should actually think about it carefully. So I hope you got some sense of curve gradient. These are three important quantities when you are studying vector fields actually. Okay? And you can play around with it. Potential. That's another. So that's something is distorting the motion. Anyway, really. Aren't these the guys, those who have made it, they don't love their kids? They really love. I can see the love being reflected from this. I don't know, this guy or the team who has, created it, how much nights they would have spent over it actually. Okay? And why they did it? To become famous, celebrity. Shahrukh Khan, Falana, to become celebrity, for the pure sake of the joy, and to show the world that these abstract things has beauty in it, so the kids can have fun with it. Okay, and that's how civilizations evolve actually. Now the situation is a bit different. you are kind of applying an external force. In other words, okay, okay. You can see it now the difference. So the previously the balls were moving because of the geometry of the space actually. The geometry of the space. But now there is an external force, a set of forces which are pushing the particles to move in the different way actually. The question is, would the curve gradient and divergence is going to be the same actually? Now you're going to see something very interesting happening actually. Think about it. If you see here, at this, in this region you have positive divergence. Take any region, positive divergence. You're gonna see you have positive divergence. But still, so it's a mix now. Now the things have bit. So you have to carefully think actually if you want to know that where you have positive divergence and negative divergence actually. Jay?
Positive divergence and zero divergence.
They're gonna, if I treat this point as a source point actually, from where the particles are emerging, then it's gonna have a positive divergence actually. Okay? It's gonna have a positive divergence. ठीक है भाई? I said to you this earlier. I think you भेजा था ना पहले. Let's have fun. Wow. This is the true random motion actually. Where the different things are playing the different role. Anyway. See you in a bit. ठीक है जी. All right. Let's get back to what it is. A little boring. If you start speaking with the equations, they give you beautiful piece of information. ठीक है जी. So now I would like to talk about another class of fields, which is called the Hamiltonian fields actually. Okay? That's another kind of a field called the Hamiltonian fields. So Hamilton was a guy Hamiltonian fields. Here's a definition. Suppose you have a map U from U into R to N to R actually. To R is a C2 smooth. When you say C2 smooth, what do you mean by C2 smooth? That is, that U and it's all kind of partial derivatives with all variables, and its second order, all kind of partial derivatives. Okay, they exist and they are continuous actually. Okay, so C2 smooth. So I know that. So we know smoothness, define smoothness, continuously differentiable. So U is a kind of a map. Obviously, this capital U is a subset of Rn. It's like a scalar field, okay, which is C2 smooth. In other words, U itself is continuous and continuous. Then its partial derivative with respect to any random variable is continuous exist and continuous, and its second order derivatives are also continuous actually. That's what the U smoothness means actually. Okay. Then I can define a Hamiltonian vector field from I can define a Hamiltonian vector field H using such a function U, okay, on U, but it's defined in this manner. H of U is basically this. So minus partial U by partial x2, partial U by partial x1, minus partial U by partial x3, partial U by partial x2, and so on and so forth. The final term is, say, minus partial U by, say, x to k, and partial U by x to k. Okay? So that's how I'm defining vectors. So take a scalar field and calculate this vector and give it a name, H of U, so that would be a vector field. It's a vector field because it takes input from R and gives you a vector actually. That's a very interesting kind of a vector field. We'll see in a moment that what amazing things this guy can do. First of all, can you guess that H is a map from where to where? R to Rn.
Rn to Rn.
Is it Rn to Rn? How many components does this?
U तो रियल वेरिएबल फंक्शन है. U जो स्मॉल था वो रियल वेरिएबल फंक्शन है.
ये real value.
तो सर रियल मतलब R से Rn तो नहीं हुआ.
Rn से Rn.
Then try and put
Rn से Rn.
So it's going to take a point from Rn, okay, and it's going to throw this into R. And if you are looking at from, okay, one way to look at it is going to be, okay, it's a map from Rn, R to R2k actually, because there are 2k vectors.
yes.
Okay, there are 2k vectors. Okay, so this is like, okay, the U is mapped onto H of U. Okay,
Yes.
but I know that U, when it takes value, it's something in R actually, and then R to R2. Okay, but if you want to see it from very elementary, from where the U starts, if you want to see H of U as a composition actually, then it's a map from
Rn.
Rn to R2k actually. ठीक है? What you can say about the smoothness of H of U? What would be the regularity of H of U? I know about U is what? Is C2 class. In other words, U itself, its first order derivative and its second order derivative are continuous. They exist and they are continuous actually. The question is, what should be the regularity of H of U? In other words, how many times I can differentiate its component?
2k times.
How many times?
2k times.
Infinite flow. We are computing the derivatives of U, so you already have first order derivatives. Okay. So you can just differentiate it one time. Okay. Because the third, if you're going to take, for example, a third order derivative of the U, I don't know that whether it exists or not, because it's just C2 smooth. Okay.
C2 smooth.
Yes. Because U is C2 smooth, so this must be C1 smooth. So this must be C1 smooth. What do you mean by C1 smooth? It's like each of the component is continuous, and if you differentiate it one more times, each component is also continuous actually. Okay. But you can't differentiate it twice again because that would be out of the regularity. We call it regularity. So whenever I'm asking about regularity, what I'm basically saying that, tell me that how many times I can differentiate this function actually. Okay. So the regularity of h of u is that it's u1 plus.
2 times derivative.
Yes, u I can differentiate it 2 times, but this guy I can differentiate it only once, not more than that. Okay? Good. Here is another interesting way to look at it. That's another interesting way to look at it.
सर यहाँ पे हम पार्शियल डेरिवेटिव किस तरह से ले रहे हैं?
अभी आता है ना, एग्जाम्पल करते हैं तो समझ आ जाएगा, डोंट वरी. ठीक है? So imagine I have a scalar field, so for a scalar field I can compute this vector. You just have to compute the derivatives and that's it. ठीक है? Shouldn't be the case. ठीक है? So here's another tricky way to write it. So imagine I have a map J. I have a map J. That is a map from R2K to R2K. Okay? R2K to R2K. Then J is doing this. It takes a point, for example, x1, x2 and xk, and it maps it onto switching the position. Minus x2, x1, okay, and minus x3, x2, and so on and so forth, minus x2k and x2k minus 1. So that's how